Hello and welcome back to the Oxford Online Maths Club. My name's James and today I'm joined again by Alice. You've met Alice before on the episode with Angels and Demons where, what did we do? We played a board game.
Yeah, you're being mean to me.
I'm sorry.
Hopefully he'll be nicer today.
Right. I brought some maths and there was a game where accidentally I set it up so that I always won all of the games. Oops. But for today, Alice has brought general relativity. So this is sort of a follow-on from special relativity, which we had last time a little bit. Or I don't know, Alice, do you want to say what the link is between, if any, between?
Well, we'll talk about it more, but they're quite different.
Right.
But special activity is included in general activity, so we find not. It's good. It's good that you've seen special activity before. We'll use a little bit of it, but we're more general today, as the
but
name indicates.
That's why they call it general. Equally, if people haven't seen the special relativity episode, that is fine. They could go and watch it. Now,
Yeah.
on the Maths Club website, which is on screen. If you found us on YouTube, we also have a website. If you found us on the website, you are now on YouTube, correct? Also online Maths Club, where we have a page which is also where I post about the reading notes. So after each after each episode, sort of like a blog, if that means anything to anyone, we post updates about other stuff that you might like if you enjoyed the episode. Underneath Alice is Slido chat, where if you're here live, you can join in. I don't know if I've set this up right. I'm going to find out by switching on the poll. And if nobody votes in the poll, then goodness knows what's going on. I think we're live. Let us know how your day was. All right, at least one person. Alice, how's your day going on a scale from 1 to 5?
Good. I'm tired. I'm good.
It's that point, isn't it? Um,
Yeah, 3, 4 for today, I'd say.
it's that point of term where I don't know what's going on anymore. Oh, I've
Yep.
broken the poll. Um, what is going on? I think I've got about 3 or 4 people in chat having a good day though. 4 or 5 stars in chat. You can also let us know in the Q&A. It says Q&A. It's for questions, I suppose, but also for things that are not a question. Your message does not have to end in a question mark. Somebody there has asked a question about co-functions, sine and cosine. I don't know. So you can also ask math questions. There is a student in there as well. An Oxford student is in there moderating chats. You've done that job before, I think, Alice. Um,
Yeah, actually, I was doing it for the special activity one.
That's it, right. So sort of swapping the roles around. We have
Yeah.
a rota of Oxford students who take it in turns to be the person in Slido chat who checks that everyone's being nice. It's a very easy job because everyone's always very nice. Anyway, I would like to very quickly mention a summer school. So the Maths Club is supported by the University of Oxford in the sense that that's where we are and they're paying us. We're also supported very generously by Jane Street. Jane Street do trading programs, and they're running a summer program for girls in year 13 or pre-university. So year 13 in England, perhaps other equivalents are available. That's happening over this summer in a variety of locations, including London. And they've suggested that I might like to mention it to you. I always mention it every year. I think I was mentioning it before. I can't remember. But anyway, here's a summer school for girls in year 13. People who love maths or computer science or both. You can find it either by typing, oh my goodness, typing all of that URL about Jane Street, but it's called Wise. And I think if you search for Jane Street Wise, you can find out about that. You don't need to be experienced in doing sort of finance or trading or something. This might be perhaps a first step to find out what all of that is like. A way to find out about careers before university. This is maybe the point where I turn to Alice and say, "Hey, have you done any career stuff?" I mean, well, I shouldn't put you on the spot like that. Right. They sent me this lovely animated GIF. Look at this. I think they've had a logo before, but in my memory,
That's really nice.
it wasn't animated. Look, so they've got like this, I guess, physics electrons moving around. Nice symmetric pattern. What do you notice about the four dots as they go round on their complicated paths? And they've got this like circuit board thing that's blinking away. Some cogs where they've managed to get the cogs. I'm always pleased when I see a pair of cogs and they're turning, like cogs rather than both the same. And then
Yeah.
the best is of course, have you seen this before? You must have you've seen this shape before, right? On the right. I think I know what shape it's based on. Which is this Mandelbrot set thing, where it's this infinite fractal zone. And I love they've managed to use because it's a perfectly repeating GIF. They've managed to set up. So
You should have a podcast about fractals. I wouldn't want to give it, but that would be a good episode, I think.
We've got a spare episode actually. There's a gap, which should maybe involve some fractals. There's an idea. Let us know in chat. And there's a question in chat. Somebody said, it's got a question mark. Are you disadvantaged if you've not done a summer school? And the answer is no. This one's in particular not about university applications at all. The ones that we run at Oxford are sort of about uni applications in the sense that we're trying to give people more skills and give them more confidence and give them more maths so that they've got more things to write about in a personal statement. There's loads of other ways to get more maths or get more things going on. For Oxford applications, we don't sort of expect people to have like named programs. I don't know, there's a sort of misconception that we might look through people's personal statement and only look for like capital letters. You know, if it's a named thing with capital letters, ooh, but it doesn't really work like that. I'm much more interested in what people got out of doing things. Even if it's all like, you know, instead of being like a capital letter summer school, it should be like spend your summer thinking about some maths. Callie in chat, thank you, Callie. Is Callie again? Good job, Callie. They're not required. Good, thank you, Callie. Right, okay, 12 votes in chat. They're having a fantastic day. 4.3. Wow, that's pretty good. I like that a lot. Rex just shouts, James. There you go. That's chat. Okay, I don't have a puzzle this week. I sometimes have a puzzle at the start. I've paused there as if anyone else wants to give us a puzzle. But
no, I don't have any puzzle to start us. Maybe someone on the chat, but I don't have any puzzle for you. Sorry.
The best I've got is I carried on thinking about clocks. Last week we had a problem about a clock, and there's the classic question of when do the hour and minute hands line up on a clock? What time does that happen,
yeah,
right?
I remember doing it at some point, but I don't know if I would be able to do it again.
Right, and it's about time, right? So time is part of.
I will see some weird clock as well in generativity.
Right, what does it mean what does time mean anyway? Right, good, okay. I'm slightly stalling. No, I'm not stalling. Oh, there is a puzzle. I've waited long enough for a puzzle to appear. A puzzle has appeared in chat. I love Maths Club. You could just wait a minute and then puzzles turn up. Fantastic. Thank you, anonymous person. So some sort of like Riddler figure, right? Where they're a mysterious puzzle person whose identity is a mystery to us. There's a good reminder as well. You can be anonymous in Slido chat. It's one of the main reasons we use Slido instead of just like gestures over here where the YouTube chat would be. Is why that's disabled. That anyway. How many different ways are there of making 6 prime numbers? Ooh, 6 prime numbers. Let's go down here. Good idea. Thank you again to Jane Street for sponsoring. They sponsor all of the episodes, whether I mention them or not. We're very grateful to Jane Street. Yes, hello. Okay, good to see you. I think I know what's going on here. Right, 6 prime numbers. But they're made from together, the digits. 1, 2, 3, 4, 5, 6, 7, 8, 9. First reaction is that's not very many digits. That's quite a lot of primes for not very many digits.
Do you need to use the 9 digits and once only? Is that the
once only?
instruction?
Yeah. So you only have 9 digits total.
Okay.
Together, use each of the 9 digits 1 to 9 exactly once. So my first reaction is like, I mean, it doesn't say how large the numbers have to be. So possibly we're making like 3 or 4 digit numbers. But that's quite greedy.
I thought we needed to... No, but we need to use the 9 digits, no?
Yeah. So I'm just thinking, you know, if hypothetically we made a 5-digit number, we wouldn't even have enough digits left over to make 6 numbers, let alone 6 prime numbers.
Ah, that's right, the 6. Okay.
I'm thinking this 6 is quite large. Okay. Oh, good stuff. So what can we do? So we need how many? At least a couple? At least a couple of one-digit numbers? Maybe 3? Maybe
Well, we
3.
can't finish with 2 or 5 because we wouldn't be, or any even number actually, we can't finish
Yeah,
with.
we've got a lot of even numbers. They're not very helpful, are they? Except for very small
I
cardinals.
mean, we can put the 2 by itself to just eliminate it, and that's one of our prime.
Am I being silly? Do we have at least 3 one-digit primes in this set? The general relativity is coming because we're getting there. Oh, is it 0 ways? Because you can't end in 2, 4, 6, or 8. Oh, chat's ahead of us. At least 3 one-digit primes. Oh, yeah, okay. I see what chat's doing. I should let Alice talk more because you were just talking about even numbers.
Yeah, you can't end with 2, 4, 6, or 8. You can't end with 5 either, right? Because you can be divided by 5. So there aren't many numbers you can end with. And then I guess we need to use the other ones, like, so you should keep 5 by itself, I guess. That's one of your prime.
Yeah, let's see if we
2
can
as
find
well.
any ways. Chat seems to think there are no ways we can do this. I'm slightly more optimistic. I think if we go, so let's get those tricky numbers out of the way. Let's go 2, 3, and 5, and then I've got 1, 4, 6, 1, 4, 6, 7, 8, 9. Okay, I've got 3 even numbers in there, but I'm planning to make those the first digits of some one-digit numbers. I don't know if those are prime, but maybe that's a way. Oh, look, in chat. In chat, away with 4. And I think you're missing a number, missing the digit 4 at the top of chat there, maybe? But hey, maybe check if 489 is prime. Yeah. Yeah, okay. People in chat who have proved there are no ways of doing this. Chill. Primes can be even. Just. Primes can end in 5. Just.
But are
I think it's
are
going to
there
be
41, 67, and 89? Are we sure they're not primes? Which one is not
I've no
prime?
idea. Maybe? I think they might be.
They're not obviously. Is 89 divided? No.
Testing my primes up to 100, right? I think 89 is prime. 67 looks pretty prime. I think 47 and 61 are definitely prime. I think I've got at least one solution. Am I enjoying mixing these around? Yeah. I probably shouldn't switch these. So putting the 1 here, I've got to put 4, 6, 8. If this is my 2-digit pool of numbers for 2-digit primes, I've got to do things like this. And then think about, I can't put 49 down, so it's going to be one of these. I can't write 69, so it's going to have to be 89. And then either of those look fine. But there's this other case. Yeah. 47, 61, 89. That looks good. Maybe I have different 3-digit primes though. This feels bad. Because then my pool of numbers becomes 1, 4, 5, 6, 8, 9. And now I think there are 4 things that are not allowed to be the last digit.
That won't work. Yeah.
4 things that are not allowed to be the last digit, so that won't work. And I don't know, but I think, yeah, there are loads of things that are not allowed to be the last digit of a 2-digit prime.
Yeah, that's a problem.
Yeah, so I think this is like no, and I think there are more possibilities.
I mean, we could still do straight digits number.
Yeah.
Maybe with what?
So if we go to 4 one-digit primes, I think that's the bottleneck. You need at least some one-digit primes. So if we go to 4 one-digit primes, which will be our last case, maybe last sort of big case, because I can't have 5 one-digit primes. There aren't 5 one-digit primes. 5 different one-digit primes. What's the pool of numbers for now? 1, 4.
Can we go on to 1 as a prime? Can we put the 1 there or not?
1's definitely not prime. Oh, I don't.
I do physics. Don't look at
Yeah,
me
okay,
like
okay, okay.
that.
I like. Whoa, whoa. I was like, oh no, is this a physics opinion? But we're about to have a massive falling out. Oh no. I still need a couple of right, and I bet there's a load of ways to chop this up, right? I think there's lots of ways to partition this, right? It could end in. No, it has to end in 9
But
or
it
1.
can only end with 1 or 9,
And I need 2 more
right?
primes. So it's going to be something ending in 1, something ending in 9, and I've got an
Yeah,
additional digit after that. So I'd have 2
yeah.
subcases, something T, something 1, something T9, and then not 49, not 69, so 89. And then I might think about 461 and 641. I don't know if those are prime. Depends what I think.
Mm,
And then final case over here, something T1, is it 41, 61, 81? Most of those are possible.
81 is
Not 81,
not.
not 81, yes, thank you. Keep going, some like branching process over here, probably loads of cases, and now we're going to think about 3-digit numbers. I think I'm not thinking about 4-digit numbers. Because a 4-digit number would leave 5 digits left over. They would have to be single-digit primes, and there aren't 5 single-digit primes. Cool. Sebastian in chat thinks that 641 is prime. That's in that case, check.
Yay.
Hooray!
Oh, we did a good job.
We did a reasonable job. I would have to now check a load of primes, right? So we've got like a solution to.
3.
Shall I guess that both of these are prime? 3, 4, and then I gave up a little bit over here, but maybe I'll commit to
There are a few
689,
solutions.
869.
I mean, the puzzle was just to find one solution, so I
Was it?
think we did
Oh, was
great.
it to find one? Right, well, we should have stopped ages ago then. Cool. Fun times. Right, okay, people are tuned in for general relativity though, so we should do some general relativity. And importantly, for Alice on the stream, expert in general relativity, with general relativity slides. So I should stop doing prime numbers. Find Alice's slides. There they are.
The slides, sure.
Yay! And I've also got PowerPoint ready for the bits that are PowerPoint. Okay.
Yeah, there are some little videos, but yeah. So the idea today is to talk about general relativity and more some consequences for some physical effects in the universe. So there's loads of nice math in general relativity related to geometry, and that's more why I'm working in the math department. But that is not really what we're gonna see today. We're more gonna see like the kind of cool effects. We're gonna talk about black holes and so on. So hopefully then you want to also come in math and do some geometry.
Cool.
So should I just tell you when to scroll, or if I pause for a few seconds, you'll scroll down?
I think if you pause, I'll scroll like that.
That sounds good. So yeah, general relativity is a theory of gravity. So where that's our starting point. And usually when you think about gravity, if you go to the next slide, you would think more about just Newton. Say when gravity is just an apple falling from a tree, or maybe that's the force that keeps you on the earth. And he wrote like a really easy formula to describe that. You may have been using it in your physics course. So that's one way to think about gravity thing. And then Newton had a great insight, which was actually that this force that you see on that slide is the same as the one on the next slide, which is the one that keeps the planet orbiting around the sun. So it's actually the same gravitational force going on. It takes a slightly more general form in that case, but the planets are attracted towards the sun. And if you generalize them, or rather, if you take this general formula and plug in the mass of the Earth and the radius of the Earth, that would reduce to what we've just seen. So the one you're feeling on Earth is just a particular case of this general formula of gravitation, which imposes that the planets goes in ellipses around the sun. And that's what had been observed for a very long time. And then Newton write this formula that explains it. That's a great success for theoretical physics at the time. And from there on, pretty much everything going on related to things falling are just described by Newton. So everyone's quite happy until Einstein. Einstein comes around and Einstein is not happy with that. And so it's gonna question Newton. No one was questioning Newton because that was working so well, but Einstein is very, as he's saying, very curious, and they don't take anything for granted. He's saying that he doesn't have any special talent. Some people may disagree with that statement, but he pretended to be humble, and he thinks that his only talent is how much he questions everything. So, what's his big insight? It's actually to sorry. So if you do go to the next slide, so what he thinks is to keep a bit of Newton's idea, but to generalize it. So what Newton tells you about gravity is that if you don't touch an object, the object keeps moving in a straight line. That's the first Newton law, the law of inertia. And then it tells you in the second law what happens if you touch it, which is the force equal to mass times acceleration. But if you don't touch it, it keeps moving in a straight line. And Einstein says, what if that's still true when gravity is present? So what does that mean? If we look at the next slide, what Einstein means by that is that actually objects moves in straight line in presence of gravity, but in a curved space. So the effect of gravity, rather than being a force, as in Newton's perspective, gravity curves the space, and then on top of that space-time that is curved, the masses still move in straight lines. So that's a completely different picture on gravity. And at that point, you may be even wondering a bit, what does that even mean to be moving in straight line on a curved space? So let's look maybe at some pictures of that.
Is this picture, just before we move on, is this picture showing a kind of curved sheet or something like rubbery sheet I think I mentioned before?
Yeah, you have the mass like sitting, and
the middle one.
It's There's some nice videos I did that wasn't really matching the theme of the slides. The other ones were too colorful, so I picked that one. But there are some really nice videos where you have like this mass curving like a space-time grid, and like the balls kind of following this curved path. Like you can even just as an experiment, like I think some physics professors do that, to just use a drape, like you just keep it tense and then you drop a ball in the middle of the drape that creates like a kind of pit, and then if you like throw all the balls on that drape, you'll see like how they turn in that pit and being attracted in the middle by this mass. So that that's a really good visualization of gravity in some sense. I will tell you about the limitation in 1 second. Maybe yeah, let's just think of this concept of straight lines first.
Yeah,
So
because you've said straight line, but that's clearly still, I mean, it's a planet going round the sun or something. It's clearly moving round and round. So
yeah,
let's have a look. Right, so, yes, okay.
Yeah, so what do I mean by straight line? So if you think of just yourself on the surface of the Earth, like you're actually on a sphere. So when you think that you're going straight, you could argue that actually not going straight because you're following the surface of the sphere. So that's what I mean by straight line. I'm following straight lines on top of my curved surface. So when I go like all around the Earth, I would have said I've done a straight line, but I'm back at my initial point because I'm going on a curved surface. That's what I mean by straight line.
Is it fair to
Or
say that
imagine,
that's like shortest route? Is that
yeah,
sort of the same
exactly,
thing?
exactly.
Okay.
So
So if
that's
I
exactly
okay.
what objects should do in general relativity. Actually, they're following the shortest path in a curved space. You may have heard the word geodesic. That's exactly what that means. I don't know if uh, that's just a keyword. If you have never heard it, now you have. So geodesic is the shortest path between 2 points on a curved space. So it looks like this curved thing.
So you've got these kind of curves over here to show if you're trying to get from up here down to here, then you would go like a straight line that maybe goes through the North Pole or something, I guess.
Yeah, so
and it's
the geodesics on the sphere are actually the big circles, they're called, like the circles that are the largest on the sphere. If you're following a line around that circle, is actually the fastest way to go between 2 points on the sphere.
a big circle.
That's a nice exercise in Riemann geometry. So that's where that's the most geometric we'll get today. That's these little pictures. Um,
There's more. We've done previous episodes on curved, like the surface of a planet. Sebastian in chat knows that there's this great internet fact that you can get from India to the USA on a straight line by sea. So on a kind of like a flat map, India to the USA, straight line would like crash into, oh gosh, geography, maybe Japan. But on the actual Earth, you can go on a weird like a kind of shortest route in the sense that any perturbation to your route would be longer. Short routes are hard to talk
yeah,
about,
yeah.
aren't they?
I didn't know that fact actually. That's really cool.
I guess we're going to
Another
have to put
one
it in the further
say
reading, aren't
in
we?
the same vibe. You know when you take the plane, if you look at the little map, it looks like the plane is not taking like the shortest route because it will go, for example, very north or something. It's actually following one of these big circles. It's because it's going around this sphere. Like the shortest path is maybe not the one you would have imagined. It is.
Although it's tricky because they optimize for wind currents and stuff. Like if you actually look on flight radar, flight tracker
Yeah,
24, then they,
okay.
they
The
do.
flights
Ah,
have to
no,
take a
okay.
bit more
They
into
do different
account,
things in
but
different
still.
directions. Yeah, it is. There's someone upstairs in Maths who's working on it. So they're working with air traffic control to do like the
Oh,
pathing
that's so
swaps. I say,
cool.
yeah, no, we've got someone in the building. Louis asks whether other forces also curve space or is it just gravity?
No, it's just gravity. Gravity is a really special force.
Yeah, and Rex
It's
wants.
a You have other models to describe other forces in physics. There are only four fundamental forces, but gravity is really the one that behaves weirdly. The other ones are mediated by particles. Gravity curves space instead. Gravity is a bit singled out. People are trying to find some theories to treat all the forces in the same way, but the current status is to treat all the other forces in the standard models that work well. Gravity doesn't fit in that. Instead, gravity fits in general relativity. So that's one point I wanted to come back at the end, but we may not have time to finish. So it's good to already mention it now. So it's out there. Gravity is weird, and gravity curves space.
Rex has got a philosophy question, which is whether gravity curves space time or whether gravity is the curvature of space time. And I think that's a philosophy question.
Yeah,
Are they just the
so
same thing? But
maybe actually there is a short sort of answer to that on the next slide, or maybe I'm just pretending it's the answer, so I move to the next slide. Let's see if you find it enlightening. But there is this quote by Wheeler. Says space-time tells matter how to move, matter tells space-time how to curve. So it's this kind of relation. I put mass, and that gives the curvature to the space-time. So maybe in more to come back more to the question, it's gravity is the curvature of space-time, so mass curves the space, and what we mean by gravity then is the curvature of space-time. I don't know if it makes sense. And
what
then
is
the way
anything, right?
that objects move in the presence of gravity is by following these straight lines in this curved space. So that's a lot of words to just say that you have a curved space and think going in straight lines there. So that was really Einstein insights to summarize and make things maybe clearer again. And so only equation we're going to see today, but that's a beautiful equation. That's Einstein's equation of general relativity. There are no other equations in general relativity. Once you've seen this one, you've seen them all. So that's really cool, I
That
think.
is
And
that is good. Well, the downside though that means that the equation itself is quite complicated. I think we're not going to explain what
yeah,
r
it's
subscript
not.
mu nu, you know,
Yeah,
points of
exactly. So I don't want to insist too much of maybe what's entering in details. One thing that One thing I want to point out is that actually this quote on top of it completely summarizes it. So on the left-hand side, this R mu nu or G mu nu, the encodes all the geometry of space-time. So these objects are called curvature tensors. Anyway, all the curvature or all the shape of how it's curved. is encoded in these objects. So that's what we have on one side. And we equal this geometry to the matter content. So all the matter, all the mass that is in the spacetime is in this object that is called T. So I put all my matter in T and all my shape in this R and G. And so I'm saying shape equal matter. And say matter tells spacetime how to curve and spacetime tells matter how to move. So through this equality. So I think it's a really cute formula for that reason. And you can see again the little constants that are left. So the G on the right hand side is the Newton's gravitational constant that we had on the previous slide. So Newton put it to say how planets were moving around the sun. We see it again here. And the C at the denominator is the speed of light that you've seen in the special relativity. And that's exactly through the presence of this C that special relativity is actually encoded in general relativity, if you want. So it needs the speed of light to enter our equation as well. So only a few ingredients, and we can do a lot with it. So the rest of the discussion will be to see some consequences that come out of this equation, basically. We won't see the equation again, but we'll see some consequences of it. So one thing is that when Einstein wrote down this equation, as innocent as it looks or not innocent, that's for you to decide if you think it looks difficult or not. It's actually dreadfully difficult to solve. It's quite easy to write down, but then to find solution to that equation is really difficult. So what I mean by a solution is a shape of space-time that solves that. And so when Einstein wrote it, it was like, okay, no one will ever be able to solve it. The only way to go about it is that there is no matter at all and the space-time is flat.
Okay.
That solves it. We have basically 0 is equal to 0 and we're happy. And it was thinking, okay, so now if I want something more complicated, even like keeping 0 on the other side, that's called the Einstein vacuum equation. The vacuum Einstein equation. So in the vacuum, I have no matter, but I could still have some curvature. Like anyway, I'm away from the mass, so I'm describing the curvature around a spherical mass, for example. So let's say I have a planet, or at some point, and around the planet the space-time will be curved. That's the gift that we're seeing before the moon will orbit the planets. The space-time needs to be curved around it, okay? So that didn't, and that's actually Schwarzschild, this guy on the picture, who came up with the solution to describe the geometry of the space-time around that. And so that wasn't Einstein. That took about a year after Einstein wrote the equation. And Schwarzschild was actually a German soldier in the trenches. And apparently that wasn't exciting enough. And so he decided to do a bit of physics instead to keep him excited. And he wrote his solution. And that's a very important solution because it describes the geometry around any spherical mass. So if I take a football ball, the Earth, the sun, or a black hole, the metric or the geometry of spacetime around it are all described by this Schwarzschild solution. So that's really pretty crazy. Just saying that I need some spherical symmetry, like I'm around the sphere, and then you find that metric around it. So Schwarzschild was a smart guy. He died a year after writing that metric, unfortunately, so he didn't come up with any more solutions. But people are still very grateful for his work, and we'll come back to it a bit, like when we look at black holes. Actually, all the effects that we're going to discuss do take place in that metric. We're only going to look at effects that happens around spherical masses, because we're always around either the Earth or the Sun or a black hole for all that's interesting for us today.
I guess that means...
And just in case you're interested in doing general relativity for your research or something, people are still looking for solutions to that equation. And you have numerical methods, and people are still, trying to solve that equations in different contexts. And now people are also using AI to do that. So there are new, interesting, exciting developments. It's been a century, more than that now, that it's out, and people are still solving it. So really cool equation. So what have we learned so far? Say, from Newton's perspective, gravity is a force, and then Einstein comes and it completely revolutionizes it. Gravity is not a force anymore. It's a the curvature of space-time and there is no force acting on the object follows this straight line as when there are no force applied in this curved space. So, okay, it's just seems like we came up with a more difficult equation. Newton was working quite well. So why do we bother with Einstein? So the people ask themselves that question. We're going to see some experimental proof, but first we can try to answer it like ourselves. So let's come with a little thought experiment. Einstein really loved thought experiments. That's how he came up with ideas. He was just imagining weird situations and trying to imagine what would happen. Gedenk experiment, because he was German. And so let's do a little one. Yeah. So the question I want to ask you, and you can try to see if you have some ideas in the chat, is what would happen if the sun was to disappear from both perspectives? So try to apply Newton's idea, Einstein's idea. Are the consequences the same? So sun disappears, what happens next?
I think I should not go to the next slide. Is that correct?
Yeah, I think the question is on the next slide.
Oh, the question's on the next slide. Okay, we're getting that one then. Right, there you go, chat.
I did a great work on the slides. Everything's on them.
Yeah, maybe you don't need me to doodle on top of the slides. What does chat think would happen if the sun disappeared? I guess I kind of have a Newton idea, I suppose. Isaac Newton tells me what happens if there's three laws for Newton, aren't there? There's the equal reaction one, that's not the relevant one. There's the one about zero force and there's one about accelerations. So.
Yeah, we want to really think about like the one that describes the force. We don't want the Newton's law, which we want, or Newton's law of gravitation. We want that tells us like what's the gravitational force. Remember, F is equal to g(m)m)r squared. That's the one we're interested in.
Okay.
So the masses attract each other inversely proportional to their distance between them. I can't really read the chat too well, so if you can read it out loud to me.
Somebody says, I'm going to scroll back a little bit so I get everyone. Anonymous says, planets orbit around Jupiter instead. Mary says, we would feel it immediately, brackets Team Newton. Sebastian said, wouldn't feel it for 8 minutes. And Anonymous says it would be quite dark, I reckon. We would all freeze.
Fair enough.
And Louis has an opinion from Newton and an opinion from Einstein, which I think would lose gravity from the sun and see it disappear. Newton suggests that planets continue in a straight line. So that's an anonymous person.
Yeah.
But they also add, we would all die. So.
Cool. Well, I guess there are loads of good ideas. People are close to the truth. That's following the steps of Einstein. We all reach good conclusions. So let's see from Newton first. So as people were guessing, once the sun disappears, the force just drops to zero. There is no mass to attract us anymore. And so indeed, instead of moving on an ellipse, we start moving on a straight line and get completely ejected out of our orbits and out in the wild universe. And that happens immediately. The sun disappears, no force, bam, we're out. But it's a bit weird if you think about it, because the sun is quite far away. So the fact that we know directly that it's gone doesn't seem that natural. On the other hand, if we now look at what would happen from Einstein perspective.
This is a video, so I'm just going to do that.
Just a little video works. Yay!
It doesn't work. There we go.
So the sun disappears, and so the curvature of space-time changes, and it takes a bit of time for the curvature of space-time to change all the way to us. Okay, the GIF is very fast because it looks like we're turning 3 times still. It doesn't take 3 years to reach us, but it would take 8 minutes, as been mentioned in the chat. So what are these 8 minutes? So if we go to the next slide, we can think about the time it would take to reach us.
Ooh,
sorry,
I've broken everything.
Pressing you.
Let's find out. No, there we go. I did it.
Thanks. So we know that the speed is distance divided by time. So the time it would take to reach us is the speeds of the information times the distance. So the sun is a bunch of kilometers away, and the speed of the information is the speed of light. Say that's how fast gravitational information propagates. That's where we connect back to special relativity and say because the conclusion is that it would take 8 minutes for us to get ejected from our orbit because the information propagates at the speed of light because nothing can go faster than the speed of light. So from Newton's perspective, the information was reaching us immediately, which is in contradiction with special relativity, whereas Einstein's picture reestablishes this compatibility with special relativity. So all is good.
An anonymous person says it reminds them of superliminal signaling, which is the idea that
Yeah,
yeah,
superluminal signaling is when sometimes information appears to reach us faster than light, but you can, if you dip a little bit further in this equation of general relativity, you see that it's just actually an effect of referentials that doesn't break special relativity. People think it does because it seems to be faster than light, but everything, all let's say that the solution is really in the word seems. It's actually not faster than light. It appears as faster than light, but it's just because things are moving relatively to each other and so on. But
there's some other
you need,
paradox there, right? But it also answers this
yeah,
question, I think, because
it seems again to be a paradox, but not the physics is not broken. I promise. But
I think that's
if they
always the way
come
with
for
physics paradoxes, right? It seems to be a paradox, it has paradoxes, but I think they mean for this
But
one
with
that
special activity, yes, both special activity and general activity are quite good at coming up with these paradoxes. And then you have tutorials with master students where you show them why physics is not broken. But I don't know, I don't think that with the scope of today, I would really go into superluminal propagation. But yeah, that does connect with this speed of information and traveling at the speed of light.
if you could see the sun disappearing straight away, then a powerful civilization could vaporize and unvaporize the sun really quickly to send us a signal in
Oh.
Morse code that we would get immediately. That's how it's, I think, related to this idea that if you could
Yeah,
get the signal
that's why
immediately, you could
Newton
use it for sending
doesn't work.
information.
Yeah,
So that's
yeah,
how
you
you know
don't.
that. Yeah,
Yeah, that Newton leads to a bunch of things not working. Like we really need special activity. Like once we figured special activity out, we didn't really give up on that. Now, like any physical theory should respect the fact that nothing travels faster than the speed of light, which is not really a problem on a daily basis. Like when you're just going and do your shopping, like you don't really notice that. But if the sun were to disappear, then you would have to think about special activity.
chat would like to know where the sun has gone in this and has it become a black hole? Could the sun become a black hole?
No, the
Not really.
sun can when the sun dies, but I mean at some point, so the sun is a star and it's burning this like so there's some star reaction and it's burning all the matter in it like it's reacting, but it's going to turn into another kind of star that is not emitting like radiation as it's just going to be a dead star. It's a bit boring. Like yeah, it doesn't have the density to turn into a black hole. I'm sorry. But you'll be dead as well, like when it turns into a dead star. It's just like you're not gonna be dead in a black hole.
Oh, that's a shame. Go next slide. Oh, next slide.
Yes,
Next
please.
slide.
Okay, so we did a good Gedank experiment, but the thing is that that was still, yeah, a thought experiment, but not an actual experimental experiment. And people do like that before approving physical theories. As mathematicians, we don't care as much, but typically physicists do care more about experimental tests. So when Einstein came up with his theory, they were like, okay, the sun is not disappearing, the equation is difficult. Can you actually give me a proof that your theory is better than Newton? And there were two proofs within the first years that were really impressive and that got people on board. So the first one relates to the orbit of Mercury. So if you go to the next slide, say from Newtonian gravity, as we said, planets are just moving in ellipses, and that just keeps going in ellipses. And but what was observed for like maybe a century at that point was that actually Mercury wasn't really going in a perfect ellipse like that, but rather every turn it was shifting slightly and not really following the same orbit the next time. Say more as on the bottom picture. And from Newton's perspective, there is no way of explaining that. So people were conjecturing that maybe there was another planet in the solar system that we couldn't see, and that's what was moving the orbit of Mercury. They even gave it a name. I think that was Vulcan. Everyone was trying to discover Vulcan, and no one was seeing it. And the reason why no one was seeing it is because it's not here. But until Einstein, and then Einstein came up with with general relativity, and general relativity just adds some bits of corrections to Newton's equations. And actually, if you do compute the orbit of Mercury with general relativity, you do find that, I mean, any orbit, but in particular the one with Mercury, does shift a little bit. And it shifts of 43 arc second per century. So that is tiny, but that is exactly what people were measuring. And then they plugged all the values in Einstein equation and they found the exact same number. So that was a big, big success because there was this mystery, and the mystery was solved like with an amazing precision as well. So people were quite happy about that one, but still the equations are awful, so people are still not completely on board. So let's look at the second proof that there was. So with this bending of light, so one thing that I've kind of, yeah, wanted to come back on and I didn't, is this kind of misleading picture when you just drop a ball on a drape. It looks like space curves, but really the statement, and that's very important, is that space-time is curved by mass. And you really need to think about space-time. So hopefully, as you talked about special relativity at some point, or maybe you're just already on board, but should really treat space and time on the same footing and think really that we live in four dimensions, three spatial one and one time one. And so really what happens in the presence of mass is that both the space and the time is curved. So actually that's a point that is important more for the next effect. But still for this one, let's look at how the space is curved. So we have the sun curving the space, and there is a star behind the sun. And say because the sorry, because the space is curved, the light that comes from the star, rather than coming in a straight line, it comes in that line that follows the sun. That's also where it's quite important that to use special relativity rather than Newton, because for Newton, light light doesn't feel any force and it would go in straight line. So you really need general relativity to for light to be distorted by the presence of a mass. So light is following a different path with general relativity. And so you wouldn't see the star at the place that it actually is in the sky. So that's one prediction from general relativity. But it's really difficult to observe because typically when you for the if you look at the figure, the star the star appears at a different place because the sun is in the middle, but the sun is quite
Right.
bright. So you typically don't see stars when you see the sun, but you need the star to be behind the sun for it to be displaced on the sky. So how do you solve that? Well, you wait for the moon to also be in the middle and obstructs the light from the sun. And that's called the solar eclipse. So let's look at where the stars are during a solar eclipse. They don't happen that often, but Einstein was lucky enough that one of them happened just 4 years after he wrote down his model. So that just left the time to be able to compute the effect of this shift within his model. And then the eclipse happened. We could measure where the star was observed compared of where it was supposed to be. And they saw it this exact shift predicted by general relativity. So
Right.
that was quite an amazing test of the theory.
I think I've heard that described as like looking through a glass of water, where everything's a bit there's some everything's a bit distorted and
Yeah,
things are not
exactly.
where you might think they are, or looking through water, things get sort of distorted there as well.
Exactly.
So in this picture, there's a solar eclipse going on, and I love the idea that there's a solar eclipse happening, brilliant, but people are not looking at that. They're trying to look past that to see the
Yeah, they
starry
should be.
background slightly distort as the sun.
Yeah, you may see like some little. dots. Sorry, I'm getting too close to the camera because I'm trying to look on my screen if I can see some little dots on the
There's a
picture.
few little dots. There's one
But
down here. There's a few around here. I don't know if those are
yeah,
like.
there should
I
be
don't know where they're
some
supposed to
stars
be.
around. I mean, you're looking at the stars
It's a photo
anyway.
from 1919, right? It's 100 years old. It's got some dots
So
on.
yeah, okay, let's move on to
Okay.
like we don't have yeah, we have maybe 10 minutes left, not
Okay.
even.
Sorry.
Let's try to cover a few
Okay. Okay.
cool aspects. So, um, do you know why you actually need GR every day? So you do use GR every day, but to maybe put it in the chat what you think it is useful for. I already introduced which effect is used, and then we'll see in which object it's actually used in practice. So the effect that we need from GR is the one of time dilation. So if you scroll down, that's not spoiling the answer yet. The answer is on the next one. So, um, so as I was recalling for the previous effect, but I should have recalled now, is time is distorted by the presence of a mass. So actually, the time is passing differently if you're close to a mass or further away. It's distorted by exactly this little square root that is the one that we're kind of seeing on the in Einstein equation already with the Newton constant, the speed of light, and then the mass is the mass for close of which you are. So the bigger the mass, the bigger the effect is, and the r is the distance you are from the mass. Say then you also feel it more when you're closer, and maybe you I don't know, maybe I'm too old. Do you still watch Interstellar? Anyway, the dad is saying is younger than his daughter at the end. Sorry for the spoiler. Maybe you have to cut it, uh, but that's because he stayed too close to a big mass, and so his time was completely like slowed down. So that's the effect that we see here. Okay, we have some good answer in the chat. That's
Yeah.
indeed for GPSs that we needed. So how does that work? Let's go to the next slide. So because the GPSs are further away from Earth than we are, their clock doesn't run at the same speed as our clock. And say when you actually use a GPS, what happens is that you're on the surface of the Earth and you send a signal away, and the signal is perceived by three satellites, and they send the signal back. Say that triangulates your position. But to know, like, basically where it has been perceived, what you want to know is like the time it has taken to like reach the satellite. So you send it at a certain time, and the satellite tells you at what time it got your signal, basically. But its clock is not running at the same time. So you need to when you need to translate that information, you need to basically readapt the clock of the satellites all the time. So if you weren't readapting the clock of the satellite according to exactly that square root that of generativity, so if you weren't taking that generativity effect into account, the clock would shift of 38 microsecond per day, which sounds like a tiny amount of time. The problem is that remember that you're multiplying any time by the speed of light to get a distance. And the speed of light is huge. So when you would be shifting by only 38 microseconds, it would actually represent a shift of 10 kilometers per day. So if you don't adapt the clock after a day, basically your GPS is completely useless. So
That's
I particularly love that example as a theoretical physicist because people keep asking you like what your research is useful for. And you can just tell them, well, Einstein didn't know that generativity would be useful in GPSs. So you kind of leave people like a century from now figure out what your very theoretical model may be useful for everyone every day. So yeah, you can use that example if you just want to do abstract stuff.
curvature of time. Such a good phrase. Sorry.
So now, yeah, we've seen that in the say when the light from the star was passing the sun, it was bent. Now we've seen that the time passes slowly when I'm close to a mass. So can you imagine what the most extreme version of that? What we've all been waiting for. Yay, you get a black hole. I hope some people had put it in the chat in the meantime,
They're
but
typing right now. But yes, black holes. Woo!
woo! So, so if you just so if you just go to the next slide, so the idea is that as we were saying, so we have a mass and the it deforms the space. And the more you have mass, the more the space is deformed. You have some fun memes with that usually. I wanted to put the meme version, but anyway, so the idea as well is that you can create black hole by having some mass that collapses. So if you have so as we were asking before, like would the sun turn into a black hole when it dies? So not the sun, but other stars would. So that's kind of how you would create a black hole. So that's a very, very dense object. And so it has different particularities. So the effect is very well known for, if you go to the next slide, is that basically once there is a point of non-return, if you want, so you can gravitate around it, but once you pass a certain point, that is called this last stable orbit, you can never come back from it. Say after that, say, or rather, the point that you cannot come back from is the event horizon. So you wouldn't actually notice if you cross the event horizon, but after this event horizon, it's actually further down the what's called the throat. So once you cross this event horizon, you can never come back. And so yeah, it's so that's where we said that even light cannot escape, and there are some weird effects related to that. That's where it also appears to be black. And actually, Schwarzschild, if we go back to Schwarzschild on the next slide, remember that's our guy describing masses, spherical masses. So he wrote that metric, and what he found is that there is something weird happening when the radius is equal to 2g times the mass over c squared. And that's actually the radius of a black hole, the radius of the event horizon. So what it means is that if all the mass is concentrated into a smaller region than that, that's what we call a black hole. So that's something very dense. And if the mass is like extending below that, like the event horizon is basically inside of the mass, so nothing will happen. So it really depends if the mass is really dense enough. So why do I have this little map of Oxford underneath? It's because if you put the value for the sun, so 2g times mass of the sun divided by c squared, then the radius that you would find, that's called the Schwarzschild radius, is 3 kilometers. So imagine that all the mass of the sun is concentrated in this little circle around Oxford, then that's what it takes to make a black hole. You need to compress the sun in Oxford, and then around that, it's what we call a black hole. And so that's very, very, very dense. That's all I want to say with that little map. If you think of the mass of the Earth, it would take the radius of a marble. So black holes are very dense.
It's that
So
density.
you
There's a
can
question in
imagine
chat which I
that's
think is
where
really
things
good.
happen.
The question in chat is whether it's mass or is it technically density that curves space time? And I think that might be onto something, right? I think it's technically the density is the thing. That the
Yes,
same mass in a very small area has a different causes a different curvature.
absolutely, absolutely.
Okay, so that
It's
T
the
tensor I'm going
density.
to think of as
It's very good.
matter as a
So
density.
maybe
Good, good.
I think we're almost done. So maybe just show the next slide
Look
that
at it,
has
look at it.
pictures of black holes, because the people got Nobel Prizes for that. So the one on the right is the one that is at the center of a galaxy, Sagittarius A. The one on the left is M87, and it was like the first picture that had ever been taken. And that really took a massive international collaboration to come up with these pictures. You needed a telescope everywhere because black holes are black. So if you just look through a telescope, you wouldn't see anything. So it took loads of telescopes to take like loads of tiny data and combine them together. So maybe that's a good point to just conclude about the beauty of international collaborations and collaboration in science, and that gives rise to these cool black holes that you couldn't access otherwise at all. I'm sorry, I had more things to say, but we took more time, which is cool as well. I guess we had more interesting chats. But yeah, if you have more questions, reach out, and I'm happy to talk more
There is
anytime.
a Math Club contact on the screen, and it's pretty guessable that it is OOMC at maths.org.uk. Thank you very much, Alice. Thank you. What a lovely picture to end on. Is this? So this is like the. Why is it not? You said black hole's
Yeah, so
black. You can't
what you
see it.
see,
What am I
yeah,
looking at?
thank you for
Sorry.
asking. So it's actually the matter that is orbiting the black hole, what you see. So because
Ooh.
the black hole is so dense, the matter that is orbiting it is orbiting with a lot of energy. It's about to fall in, not fall in. Like that's a very intense region of space-time, as you can imagine. So it's actually emitting some radiation like that. Say it has a lot of energy, and so it's emitting that radiation, and that's what you're observing, which is obviously not orange, that's just energy, and then people translate this energy frequency, they give it a color, and that's what you see on the picture. But yeah, that's what you would be actually capturing uh, on the telescope is this energy radiated by particles orbiting the black hole.
Right.
And
Okay.
that's
Oh,
what
a
you
little bit like. So not the same as, but a little bit like with the eclipse, where we're not looking at the eclipse, we're looking at the effect of the eclipse on the visuals,
exactly.
and here is the visuals on also the stuff that it's affecting directly. So a little bit more interactive than the stars seen past the eclipse version. Excellent. Adam says thanks, Alice. Good. Um, I think we're going to call it there for time, if that's all right with everyone. Lovely picture to finish on. Alice, anything you want to say at the end? Anything you want to? We'll put gravitational waves, I think, in the further reading notes.
Yeah, there's some gravitational waves. Uh, and yeah, loads of Nobel Prizes around black holes for experimental stuff, but also when they got some experimental Nobel Prize, there was also a part that was for theoretical contribution to black holes, which was awarded to Roger Penrose, who has his office in this building. You may bump into him at Sainsbury or around the canals in Oxford. I've seen him both places, and it's quite cool to be as close in Oxford as we are to someone who actually got the Nobel Prize for black holes. So that's maybe one thing that is also nice to mention.
Jet says bye and thank you. We will say bye and thank you. We'll be back in 167 hours for another episode of the Oxford Online Maths Club. But until then, have a lovely evening, have a lovely weekend, have a nice week. Take care. It's bye from both of us. Bye.